created by MindSticks Foundation Trust.
Namaste, students, and welcome to today's Explainer. Today, we're going to embark on a really fascinating geometric journey all around the circle. We'll be taking it at a nice, comfortable pace. We are going to cover touching circles, understanding circle arcs, measuring those arcs and angles, congruent arcs and chords, and finally introducing inscribed angles. Let's get right into it.
Section 1. Touching circles. So I want you to imagine what happens when two completely independent circles meet at exactly one single point in space. Just one tiny dot of connection. We actually have two ways this can happen. We can have externally touching circles, where they just kind of bump into each other on the outside, or we can have internally touching circles, where a smaller circle rests neatly inside a larger one. But here is the really interesting part. In both of these cases, they share exactly one common point of contact and a single common tangent line that passes right through that exact spot.
Now let's formalize this observation into a proper, strict mathematical theorem. The theorem of touching circles states this. If two circles touch each other, their point of contact lies on the line joining their centers. So the absolute crucial takeaway here is that whether those circles are touching on the inside or the outside, if you take a ruler and draw a straight line connecting their two centers, that line is going to pass perfectly through their single point of contact. It's just a wonderfully elegant rule of geometry, don't you think?
Section 2. Understanding circle arcs.
All right, let's bring our focus from two circles down to just one single circle, specifically looking at its curved edges. Imagine a straight line cutting right through our circle, like a knife slicing through a pizza. In geometry, we call this a secant line. Notice how this secant line cleanly divides the entire circle into two distinct parts. Well, these separated curved portions of the circle's outer boundary are what we mathematically call arcs.
But you'll quickly notice that unless the line goes exactly through the middle, the two pieces aren't equal, right? That's why we categorize them. We have a major arc and a minor arc. The major arc is the larger chunk. It's the curve that actually sits on the same side as the circle's center point. The minor arc, on the other hand, is the smaller curved portion on the opposite side of the center. And just a quick tip, to keep things simple, we usually just use two endpoints to name a minor arc.
Section 3. Measuring arcs and angles.
Okay, now that we know what an arc is, how do we actually calculate its measure? I'm going to slow down just a bit here, class, because it is absolutely crucial you grasp these formulas for your exams. To measure an arc, we look at the angle formed right at the center of the circle. First, the measure of a minor arc is exactly equal to its corresponding central angle. Simple enough. Second, for the major arc, you just take the full circle's 360 degrees and subtract that minor arc measure. Third, a semicircular arc is exactly half, so that's 180 degrees. And finally, the whole shebang, a complete circle, is a full 360 degrees. Make sure you memorize these.
Section 4. Congruent arcs and chords.
Let's move on and explore how these curved arcs and straight lines inside the circle relate to one another. But before I just hand you the rule, let me ask you a question. When can we confidently say that two arcs are completely, 100% identical twins? Is it enough for them to just have the exact same angle measure at the center? I want you to think critically about this for a second. Well, here's the absolute mathematical truth. For true congruence, two arcs are identical only if their angle measures and their radii are equal. So simply having an equal angle measure of, let's say, 40 degrees, that's not enough on its own. The circles themselves must be the exact same size. Their radii must be completely identical for the physical curve of the arc to match perfectly if you were to place them one on top of the other. And this brings us to a really beautiful connection between straight lines and curves. We have two very powerful theorems here. First, if you have two congruent arcs, the chords connecting their endpoints, those straight line segments, are also going to be perfectly congruent. And the exact reverse is true as well. Arcs corresponding to congruent chords are congruent themselves. It is like a perfect geometric mirror, bridging the gap between curved edges and straight lines inside our circle. Section 5. Introducing inscribed angles.
Class, prepare yourselves, because this final concept is perhaps my favorite part of today's lesson, and it really sets the stage for some advanced theorems. Earlier, we measured central angles, right? Where the corner, the vertex, sat exactly at the circle's center point. But what happens if we pull that vertex all the way back until it's resting directly on the circle's outer edge? The arms of the angle still reach out and cut across the circle, but the starting point is moved. This specific type of angle, sitting right on the boundary, is what we call an inscribed angle.
So, as we wrap up our explainer today, I want to leave you all with a bit of a mathematical puzzle to ponder before our next class. We know for a fact that a central angle is exactly equal to its intercepted minor arc. But if we've pulled that vertex all the way back to the edge to create an inscribed angle, how do you think the measure of that angle relates to the arc it cuts across? Think deeply about it. It's a real game changer. Keep asking questions, keep studying hard, and thank you so much for learning with me today.